So here we go. This is what we had talked about in the last class. We talked about how kind of a line graph is set up, the names of the axes, the fact that the origin is the spot in the middle, which is the 0, 0 location. And then I talked about the independent and the dependent variables, kind of what those mean. And then I gave some different terms to them, manipulative and responsive, because again, I think those are a little more descriptive. So the manipulative variable is the one that you are making some changes to. And the responsive is the one that, the beeps. And the responsive is the one that is going to react or respond to whatever this manipulation is that you did. And so again, there was an example in class I had given about plants and how if you take a certain number of plants and you decide, hey, I wonder if exposing those plants to music affects how they grow. And so we had talked about having, maybe rock and roll for one plant playing, and then maybe some classical music playing for another plant, and maybe some country and Western music playing for another plant, and then maybe a fourth plant that no music at all is playing for. And we would call that one the control group, because that group is not having anything changed. Like that plant is business as usual, no music, just whatever you would do to take care of a plant normally. And again, that control group is kind of important because we can compare what no music looks like and how the plant responds versus 3 different kinds of music. So in that example, which one of those is manipulative and which one is responsive? So manipulative, most of the students were able to wrap their head around the fact that the manipulative is the type of music that you picked. You're changing the music. You are manipulating that there's different music for the plants. Now, the responsive variable, what do you think is going to depend on or respond to that music? So the responsive variable in that case would be the plant growth itself. And so you might even, keep data. Maybe every day you would measure the height of each of the plants, and you would keep track of that every day. And then by the end of the experiment, you could have a graph full of data that each of those lines, you could have a line on your graph for each of those plants. If you have a bunch of height data, height of the plant, and you took that for every day, then on your line graph, you might have, the days going by across on the X. Now, again, I know that that's not the time every day ends up being on the X-axis and not what we said music was the manipulative. And so how do you put music on the X-axis? How do you put like rock and roll here, and then you put country music here, and you put classical music here, and then you put no music here. So instead of that, since your data was collected over a period of time, we would probably have to put days down here and then the height of the plant here. And then you might see the lines kind of going zigzagging across the grid here. And then maybe we could determine which was best. Maybe no music was best. Maybe there was no difference in any of them, and all of them have a very similar data. I don't know. We would have to do that and then find out. But the point of that is that there are manipulative variables, things that you change, and then there are responsive variables, which are like the effect. You got the cause and the effect. The cause is the manipulative. The effect is what changes because of what you manipulated. I hope that makes sense. Now, then I drew everybody's attention to this data right here, which was the worksheet I posted on Classroom. So we have here some data for heights of buildings in meters versus the number of stories that those buildings have. Now, the thing I asked in class was, let's say you're a hotel owner and you want to build a new hotel. when you contact the builder to start this process, do you think you tell the builder how tall you want the building to be? And then he tells you how many floors you can fit in there? Or do you tell the builder, this is how many stories I want, this is how many floors I want, because I know how many rooms I want in this hotel. I know that each floor can have 20 rooms, and I want 100 rooms total, and so I need 5 floors, 5 stories. And then, so you determine how many stories there are, and then the height of the building just happens. It happens because of how many stories you built. So which way do you think it would be? Do you think you tell the builder, hey, I want a 20-meter tall building. You tell me how many floors can I fit in there? That doesn't seem like that's the way it would go. It seems like it would be the other way, where you decide, hey, I know how many rooms I want. I got this many rooms per story, and I want this many total, so I'm going to need 5 stories or 8 stories or 15. I need 15 floors in this hotel to have the number of rooms that I want. I think that's probably what's going to happen, which means in that scenario, which one of these is your manipulative? Which one are you making the decision on? Number of stories. I would say the number of stories is your manipulative. Manipulative, right there. Number of stories, manipulative. That means that the height of the building has to be what? That's responsive. The building height is going to depend on or respond to how many floors or stories you decided you wanted in your hotel. Now, this then tells us which axis these have to be on. Deciding that, figuring that out, now we know which axis each of these variables has to be on. And again, that's something you're going to have to remember, like this right here. The responsive goes on the Y, the manipulative goes on the X. So we can then label, oh no, oh boy, I wonder, oh no, I don't know if this is going to work. I need to extend this. Oh no. Well, oh boy, this is going to be interesting. I don't think I can get, oh, I know what I can do. This thing, see, there is a toolbar. There we go. Oh my gosh. Whew, that was close. I thought I was going to have a major problem. Okay, so on the x-axis, we decided it's the number of stories. So number, the pound sign is the abbreviation for number, in case you didn't know. It's not hashtag, it's a pound sign. So number, oh dang, number of stories. Number of stories measured in, I guess, stories. I don't know what unit of measure you would put on that. And then that means that the responsive was the height of the building. So then I put height of building over here. Height of building. And that's measured in meters. Okay, now the next thing about setting up a graph is that you need an interval. An interval is how much value each box, each grid box or line on the graph has a certain value. And you need to determine how much value that is. Now, on this grid, I have like a 19 by 19 grid here, all right? Because you have graph paper, you can make it as any size you want. So you're not necessarily limited in the number of boxes. I guess you are limited because your page only has so many of them. But you can make your grid bigger, you can make it small based on, I guess your preference. But in this case, if you look at my data, the number of stories, I have to go up to 12 total is my biggest value of number of stories, and that's going on the x-axis. If I only have 19 boxes to get across here, what do you think would be an appropriate interval for that? If I have 19 boxes and I have to get up to 12, I think my only option is to go by ones. I think I have to go by ones across that axis. So I might do something like this. Now, you might be thinking, well, he just said he was going to go by ones, but he went by twos. No, I only wrote down the evens, but every grid box is worth how much? 1. All right. I went by ones, but I only wrote down the evens. It's just saving some space. Otherwise, if I write down every number on every grid line, it gets to be a mess in there. All right. So again, if you're trying to remember or figure out what your interval is, it's not just the numbers you see. It's the value of each box. And notice they're all 1. 1 here, 1 here, 1 here, 1 here. Very common mistake is that the first box is a certain value and then all the rest of them are different. You can't do that. The grid boxes have to be the same value all the way from 0. Oh, which reminds me, that's 0. The origin is the far left on this graph. Now, I look at my height data. It has to get up to 35 total. And again, I've got 19 boxes here. Now, do I have to use all 19 boxes? No, I didn't use all 19 boxes on the x-axis. I've got 7 boxes over here left. So it's not like I have to use all of it, but I don't want it so compacted that it's just too cramped. Like for instance, since I have to get to 35, I could go by 5s. Now, if I do that, if I go by 5s, 5, 10, 15, 20, 25, 30, 35. I used less than half of my grid. I feel like that my data is kind of squashed. I don't think 5s would be a very good interval for me here because I have so much grid available. I would like to spread out the data as much as I can so it's not so squished and cramped. So I would not use 5. Now, someone suggested 3s in class, which I'm not a huge fan of, but I'll do it. And so 3, 6, 9, 12, 15, 18. Now notice, I'm not writing down every number again. I'm counting by 3s, but I'm only writing down every other value. So 18 and then 21, 24, 27, 30. Oh gosh, I can't even count. 27, 30, and then 33, 36. Now, because my interval is 3s, I have to remember that when I'm trying to put my data points in there, I have to remember that each box breaks down into thirds. Okay, again, to get from 0 to 3 in the first box, if you remember that's 0, then that's 1, that's 2, that's 3. So I'm having to break my boxes down into thirds. If you went by 4s, then you would have to break your boxes down into fourths. And if you went by 5s, you have to break your boxes down into 5. So this whole estimating thing we've been working on, guessing in the gap, it's going to be very important when it comes to setting up your graph. Okay, so that's all set up. Now I got to plot my points, right? So plot my points. Oh my gosh. Okay, 3, 310. 310. 3 over here. 10. Oh boy, that's 9. 10 is about a third of the way up to 12 from 9. So right about there, 310. And what was the next one? 5, what? 5, 16, and then 721. 5, 16, 721. 5, 16. 5, 16 is a third of the way up to 18. And 721 is, oh, look at that. That's on a grid. How about that? That's on an actual grid intersection. 721, since I went by 3s. And 926 and 1235. 926, 926 and 1235. 926, which is 2/3 of the way to 27. 926. And oh, come on, get on there. And then 1235. Now 35 is 2/3 up from 33, 1/3 down from 36 on the 12. Okay, there we go. So there's my data. Okay. Now, here's what we do with that. We do not connect the dots. Okay. We draw what's called a line of best fit. It's a line that follows the data. Right? It follows the data in a way that you could almost erase all your data points, and the line now represents your data. Okay, you're trying to draw a line in a way. It's kind of like an average of all of your data points so that you could just erase them all Each individual data point doesn't matter anymore. Now you have a whole line that represents all of your data. So here's how I would suggest doing that. A straight edge is critical. And I would put the straight edge beside your data in a way like this. Let's see. Let's go with my line tool. Oh, let's go with my orange. So since I have a straight line tool here on my board, I put that line there on the board, and I'm trying to make the line parallel to my data, parallel. Okay, I want it to look like it's running parallel with my data. Then once I kind of adjust it, because if I do this, if I kind of adjust it like this, I think it's pretty clear that's not parallel. It's getting further away from my data up at the top, and it's getting closer to my data down at the bottom. That's not parallel. Again, I need to slide this up this way a little bit so that I want it to be about the same distance away from all my data. Again, so it looks like it's kind of parallel. It won't be perfect, but again, that's what we're going for, parallel. Then slide your ruler over so that it's literally in your data, like amongst your data, like so. That right there, and then draw your line. Now notice, my data points are not perfectly on my best fit. Now, I'm hitting 2 data points close to their middle. Then I've got a data point above, and then one below, and then one above. So I'm trying to split right through the middle of where all my data is. It's not all on the bottom side. It's not all on the top side. I've hit a couple points, and then some are above and some are below. So I'm trying to split right down through all of it. That makes a good best fit. All right. Now, a question I might ask, and I asked a couple of these in class. What if I wanted to know how tall is a 4-story building? How tall is a 4-story building? So you would look at your graph and you look at where 4 stories is. Well, 4 stories is right here, right over there. And so if I want to know how tall that is, well, then I would take my pencil, or in this case, my marker, and I would start at 4 stories down here, and I'd make a little dashed line up to my best fit. And then I stop when I hit my best fit, and then I hang a left. I hang a Louis over until I hit the y-axis. Now, what value is that? Well, if the line right below it is 12, and this one up here is 15, and again, I'm breaking mine down into thirds, right, because I went by 3s. So that, to me, looks closer to the 12 than the 15. So that's got to be 13. I mean, in my mind, that's got to be 13 meters. 13 meters would be the height of a 4-story building. So how tall is 4 stories? And for me, that's 13 meters. Hopefully your graph is similar. If it isn't, then maybe you didn't guess very well, because you got to remember, only one of these data points was on a grid intersection. That one should be exactly in the right place. The rest of them were in between gaps. If you're having to put a data point in the gap, what are you doing? You're guessing in the gap, like we talked about with measurement. You have to guess in the gap. That means all your data points are a guess. How about your best fit line? Is that a guess? Yes. And not only that, the 4 was a grid line, but this up here, the 13 going across, that's a guess as well. So there's a lot of guessing involved here. So your graph, it may not tell you exactly 13 meters. So if this was a question on a test or a quiz, there's not going to be just one right answer. And when I grade yours, I'm going to have to look at what your graph looks like to see whether or not your answer is right. And it may be different than mine because your graph looks different than mine because all of us guessed to get to where we are. And all that guessing is going to create some differences in answers. Okay, I got to keep moving. Now, that's reading the graph. Let me ask you another question. What if what if I have a building that's 30 meters tall? Do we have any data for a 30-meter tall building? No, we've got 26, we've got a 35. Did we have any data for a 4-story building? No, we had a 3 and a 5. We didn't have 4. We have a 26 and a 35. We don't have a 30-meter. That's what line graphs do really well. Line graphs can make predictions really, really well. Bar graphs can't do that. If we'd have drawn a bar graph of this data and each building would be its own bar, then the bars would just look like the buildings, and then it would just, we would compare. Oh yeah, that one's taller than that one. Well, that doesn't tell us anything. See, the line graph, you can connect between data and even beyond data. I could ask you about 14, 15, 16, 17 stories and look up here on my graph and figure out how tall those would be. And that's beyond my data. So in this case, I'm asking, how many stories would a 30-meter tall building have? Okay, let's see. Stories in 30 meters. That's the question. How many stories in 30 meters? And so you would go to your graph again at 30 meters, which is what I gave you. Last time I gave you 4 stories, you went to 4 stories and started drawing a dashed line. Now, instead of telling you how many stories, now I want to know how many stories in a 30-meter tall building. So I go to 30 meters right here, and I start drawing my dashed line over all the way to my best fit. I stop at my best fit and I bring it down. And I bring it down right here, and it looks like I am a little wavy there, but I'm just beyond 10. So if it's a 30-meter tall building, it could likely be a 10 or 11 story building. I don't know. It's hard to say. You can't have a fraction of a floor. I guess maybe your foundation is just really tall, and it's 10 stories with a really tall foundation, and so the first story is sitting way up above the ground. Maybe it's that. But this is basic graph reading, okay? When I give you one variable, like I gave you stories at first, and then you had to find the height. The second one, I gave you the height, and then you had to find the number of stories. So this one, again, it just erased it. 10/11 stories, something like that, if it's 30 meters tall. And again, I lost part of that. Anyway, okay. So I hope that's making sense. Here's the last thing we need. The last thing we need from this graph. It's something called slope. All right. Now, do you know what slope is? There's a phrase in math class. Now this is the steepness. Okay. Slope is a measure of the steepness of a line on a graph. The steepness is what we call slope. There is a 3-word phrase in math class that we use to describe what slope is. It's blank over blank. Now you may be thinking it. You may have thought of it already. Blank over blank. Rise over run. Now, here's the thing. The steepness of the line is going to tell us some really important information. And so we need to know what the rise over the run is, and that steepness can then help us figure out something about this data. So that's what we have to do next. And I know this video is getting long, and maybe I should pause this and make a second video. Oh my goodness. I'm going to pause this and make a second video because this is getting too big. Don't go away. There will be another video coming. I hope everything so far has made some sense. We'll see ya.